Okay, welcome back. So in lecture 24, we introduced two of the standard container classes that the standard C++ library provides, namely the vector and the set. We also talked about iterators and the auto keyword and the range for loop. What we're going to do now in lecture 26 is to take a look at standard library algorithms that can be used with these standard container classes. Now, there are about another 10 or 12 containers that we haven't had time to talk about, so we're mostly going to be concentrating on looking at examples involving vectors, and we'll also take a look at some examples involving sets as we go through this week's material. All right, so altogether there are over 80 standard algorithms, and these range from being able to do simple things like looping through and copying and transforming elements in a container such as a vector. We can also do more complicated things like searching, sorting, comparing within vectors or comparing one vector to another. We can do things like binary search in a sorted vector. We can merge, compute lower and upper bounds, or figure out, I should say, the lower and upper bound of some kind of sorted container, and on, shuffling, rotating, permuting, assigning, figuring out the set union, blah, blah, blah. All right. Now, most of these algorithms take some kind of function or so-called function object that specify the details of what we're trying to do. So, for example, if we are trying to search within a vector for something, we could search merely for a particular element value, but we could also search for some element that satisfies some criterion, such as an element that is an odd number or an element that is a negative number or something of this kind. And so in a case like that, we need to feed in a function to the algorithm, or a so-called function object, or a so-called lambda expression, some form of comparison function or organizing function that we can use to drive the algorithm. All right, so that's kind of hand-wavy. So let's get into some details here. The first algorithm we're going to look at in detail is an algorithm called for each. And what the for each algorithm does is to apply some operation that you specify as the third parameter to the for each algorithm to each of the elements within some range, and the range is specified by beginning and ending iterators. All right, so we say for each, then we specify the beginning iterator and the ending iterator for some range of values in a vector, in a set, in a list, in a double-ended queue, whatever the data structure might be. And for each one of the elements within that range, we're going to perform some operation. Now, for the for each operation to work, for the for each algorithm to work, the operation has to have this kind of form. That is, it has to be a function or function-like thing that takes a reference to a container's element as its argument, and that does something either with that element or to that element. The function should return void. All right, so all of the interaction with the element happens within the function, within the operation, and there's no return value from this. Let's take a look at some specific examples. Here I have a file called algotest.cpp that you can find in the code examples. And I've defined 4 different operations that we can perform on elements in a container. First of all, I have just a very simple function, putInt, that receives a reference to an integer constant and simply uses cout to display that integer value with a space afterward. All right, so in this case, the putInt function promises that it's not going to modify the element that it receives by reference. Instead, it's merely going to print that element out to the user's terminal. This next function is called mod4. Notice that the parameter here has been declared as a reference to an int that is not const. And what this mod4 function does to each element that it receives a reference to is to replace that element's value with itself mod4. So if the element value is 7, that element value gets replaced with 3. And if that element value is 0, it gets replaced with 0, and so forth. All right, so these are simple functions that we can pass as operators to the for each algorithm. We can also pass template functions into the for each algorithm. And here I've created a template function, putT, which is able to take a reference to some arbitrary data type, constant, and whose job is to simply display that element value on the screen. So with putT, I can invoke putT by saying putT and then int in angle brackets, or char in angle brackets, or double in angle brackets, depending on what type of thing is contained within, let's say, the vector whose elements I'm interested in displaying. addm is another example of a template, but here, rather than creating a template by a data type, we're creating a template based on some integer value. So this is a new form of template that we haven't talked about before. What this function is doing is, into the element to which we've received a reference, we're adding in whatever value m has. So when I call this function, I say addm angle bracket 3, for example, and that will add 3 to each element. Or I can say addm angle bracket 15, and that will add 15 to each element. Or addm angle bracket -7, and that will add a -7 into each element. So let's see, let me scoot these over to the other side here. I'm going to lose my highlighting, but that's all right. All right, so here is these same 4 function definitions. Notice that in order, in order to use the standard algorithms, I need to include the algorithm header. And let me actually pull up a live terminal in which I'm writing this code. Okay, so this is my file, algotest.cpp, and I'm including my usual collection of headers, iostream, also vector and set, because I want to be able to create and interact with vector objects and set objects, vector and set collections. And here is my include of algorithm so that I can use the for each algorithm. Here are the 4 functions that are shown on slide 4. And then we have some other functions down below that are shown on later slides. Now, here's my code shown on slide 5 here. And I'm going to comment out all this other code so that it doesn't trouble us for this example. All right, so here's my main function. And what we're doing in main is creating an integer vector, a vector of int called v1. I'm putting some values into v1. And then I'm getting the begin and end iterators for that vector. So my range is going to be right from the beginning of the vector all the way to the end of the vector. And in this first for each algorithm, all I'm doing is calling putInt on each one of those values. Okay? Now, putInt remember, is an ordinary function. It turns out that when you give the name of an ordinary function all by itself with no parentheses after it, the behavior is a little bit like using an array name with no square brackets. So the name of a function with no parentheses afterward is actually the address of that function in the code area. All right? So the for each algorithm is going to apply that putInt function by calling the putInt function for each one of the elements starting from v1b all the way up to, but not including, v1e. Remember that the end iterator is one past the end of this vector. And so putInt is just going to be called and print out each one of these values with a space separating them. All right, so that's the first thing that happens. The next thing I'm doing in the second for each algorithm is I'm calling mod4. Once again, I'm passing in the address of the mod4 function as the third argument to for each, and consequently for each element starting from the initial element at v1b up to but not including the end, v1.end, I'm going to replace the element with its self mod 4. All right, so the initial values in v1 are 0, 2, 4, 6, 8, and so forth. And so when I do the mod function, mod 4 function, I'm going to get 0, 2, 0, 2, 0, because those are the mods of those first 5 values. And then, of course, I'll have these remaining 5 values as well. And I'm calling putInt again then to display those modified values. Okay, so that's what's happening in the first section of code, and then in the second section of code here. Now, in the third section of code, notice that instead of using v1b and v1e directly as my beginning and end, I'm doing basically an iterator addition. Turns out you can add an integer to, well, I need to be a little bit technical here. For a vector, these iterators are what are called bidirectional iterators. That is, they can move forward or backward. And so by taking the begin iterator and adding 2, that means I want to actually start with the sub2 element in the vector. And by taking the end iterator and subtracting 2, that means I want to go up to but not including the second to last element. So in other words, this reduced range here is going to modify, or is going to interact with, I should say, these 7 values. All right, the first 2 are going to be skipped. The last 2 are not going to be used, and we're going to do a put_t of int function. Notice that's our template function on each of the values. Now, I just noticed I forgot this rather important part here. All right, so from the sub2 element up to but not including the last 2 elements, what I'm going to do is I'm going to add 9 to each element. So I'm I'm sure I can say this. I'm instantiating this addm template by providing 9. And so what that means is that addm is going to go through one element at a time and add 9 into each element. All right, so let's see what we get from executing that part of our code. Okay, so I can say g++ dash standard get c++ 17, and if I were on a Mac, I would also need to say standard lib gets libc++, but I'm not on a Mac, so I can leave that part out. And then for the output program name, it's just going to be algo test. And the source code file that I need to compile is algotest.cpp. Okay, that succeeded, and so now I'm going to run algo test. And okay, so let me move forward in the left-hand slide to look at the main function again. Okay, so I'm creating the vector v1 with these values, 02468, 029407, and in this for each line, I'm just displaying those values. Then here I'm replacing each value with its self mod 4 and displaying that result. So I get 02020, and then continuing on, 0 mod 4 is 0, 2 mod 4 is 2, 9 mod 4 is a 1, 4 mod 4 is 0, 0 mod 4 is... All right, I think I made some mistakes along the way in there. All right, so 0 mod 4 is 0, 2 mod 4 is 2, 4 mod 4 is 0, 6 mod 4 is 2, 8 mod 4 is 0, 0 mod 4 is 0, 2 mod 4 is 2, 9 mod 4 is 1, 4 mod 0, 4 mod 4 is 0, 0 mod 4 is 0, 7 mod 4 is 3. Okay, I think I got through it that time. All right, so that's what the mod 4 function did. And then in the green for each here, I added 9 by making use of my addm template function. But I only did that to the elements between the first two and the last two. All right, so I only added 9 to these elements here. So 0 plus 9 is a 9, 2 plus 9 is an 11, and so forth. And so that illustrates what's going on with the for each algorithm. Okay, we specify a beginning iterator and an ending iterator, which is one past the end of what we want to interact with. And then we specify an operation, which may be an ordinary function like put int or mod 4, or which may be some kind of template function like addm of 9 or put of int. All right. Well, so that's for each. Now, transform is another very important general algorithm to talk about. So let me move ahead to transform. And obviously you say transform to run this transform algorithm. The difference between transform and for each is that in for each we specify a beginning iterator and an ending iterator and some operation that we want to do. Transform, on the other hand, stores the results into some output range that may be a different range from the input range. All right, so the input range is specified by the first two iterators, the beginning of my input range, the end of my input range, and then I specify the beginning of the output range. And it's up to me to make sure that the container where we're specifying the output range to go is at least as big as the number of elements in the input range. If I have a vector of 10 items and I try to do this transform and put the output into the beginning of a vector with only 4 items, well, that's at some point my program is going to crash because I can't write 10 values into a vector that's only capable of containing 4 values. The interface to the operator function for transform is also different from the operator function for each. Let's go back to for each. Remember that the operator for each looks like this. The operator receives a reference to some type of object, and it returns void, and it will interact with that object directly through the reference. The transform operation, on the other hand, takes an element by value, performs some operation on that element, and then returns some modified value which has to be of the same data type as the input argument. Okay, so transform takes an operation that takes an object by value and that returns a value of the same type when it's finished. And so here we have some illustration of functions that are appropriate to use with transform. I have a template function called times n. This is parameterized by the integer value n. And what it does is to return as an integer the current integer element read from the range, which might be a vector or a set. And each of those elements is multiplied by n. Okay? Add n is very similar to times n, except that it returns the value of the current element plus n instead of times n. And finally, as a third example, we have an ordinary function called sine of. What this function does is to return an integer which is either -1, 0, or 1, depending on whether the current element that we're looking at is less than 0, okay, in which case I get a -1, or the current element is greater than 0, in which case I get a 1, or the element is 0, in which case I get a 0. So this is only returning to me an indication of the sign of each element, not anything about the magnitude or some product or sum involving the element. All right, so let's walk through some examples of this. Here's my example code. Once again, let me put my functions times n, add n, and sine of on the left, and I'll pull my code file over here on the right. And now we're looking at, let's see. Okay, so we're looking at this part down to here. Okay. So, this time I'm declaring and initializing a vector event named v2, and here are the initial values for it: 129 minus 40 minus 37827. I'm getting the beginning iterator and the ending iterator. Now, I haven't talked about what auto means, but I hope you remember that auto means that we're going to ask the compiler to figure out for us what the data type returned by v2.begin is. I could type that out manually, but it's a pain. I could say vector int : iterator v2b, but for goodness sake, I don't want to type that, so I'm not going to. Then I'm also creating another vector v3. Notice that the form of constructor I'm using for v3 simply takes one integer argument. That means that v3 is going to be allocated to be of that size. Now I'm careful to make v3 the same size, the same number of elements as v2, and each of those integers will be initialized with the default value for an integer, which is a 0. All right? So up here, I've got 5, 10. I have 10 values in v2. v3 also contains 10 values, but those values are all 0. Okay? And then I'm getting the beginning and ending iterator for v3 as well. Okay. Well, the first thing I'm going to do is I'm going to just use plain old for each to go through and display what's what's in V2 and what's in V3 to confirm that they contain, in the case of V2, 1, 2, 9, minus 4, 0, etc. And in the case of V3, it should be all zeros. Then I'm going to use the transform algorithm that we've just introduced, reading data from V2, starting from the beginning of V2 and going up to the end of V2, except, one shy of V2.end. I'm going to add 3 to each of those elements, and the result is going to be written into this vector starting at V3b. Then I'm going to use for each again to display V3b, and I should see that V3b now, instead of containing a bunch of zeros, contains 3, 5, 12, minus 1, 3, 0, and so on. So let us execute that part of the code and confirm that that does what I claim. All right, I'm going to save it. I'm going to execute or compile it, and I'm going to execute it. And here we are. All right, now those first 3 lines of output came from the first chunk of code. These lines of output here are from the code that I just executed. We first created V2, containing 1, 2, 9, minus 4 up through 7. We then created V3, a vector of the same size but filled with 0. Then we displayed V2 and V3, and sure enough, we saw that V2 contains the values specified in the curlies, these, this curly brace initialization here, and V3 just contains all zeros. Following this transformation, where add n of 3 is applied to each value in the range for V2, V3 now contains what I said. It's basically the same element values as V2, except with a 3 added to each one of those values. On slide 10, we have a few more examples of transform. So let me pull those up in my live code file here. And I'll move this comment down. All right, so this time we are, this time we are modifying V3 and putting the results back into V3. So notice that the input range is from the beginning to the end of V3. The output is also going back into V3, and this is fine because each one of these transformation functions takes a value as input and returns some result as output. So it's not a problem to fetch an element from the vector V3, do some computation on that element, and then put the result back into the same slot in V3. So this works just fine. In this first transform here on slide 10, we are computing the negative of each of the values. Then in the second transform, we're also modifying V3 into itself. We're adding 5. And finally, in the third transform here on slide 10, we are getting the sign of each of the item values in V3. So let's take a look at the output from this. Okay, so here is the final line of output that we got from slide 9, and that was the same contents as V2, but with 3 added to each value. All right, so we had 4, 5, 12, minus 1, etc. Now we're computing the negative. All right, so this line of output using our for each algorithm, sending things to cout with put t of int. This line of output is the negative. There we go. This line of output is the negative of what it was before. This next line of output has 5 added to each value. All right, so instead of -4, we have 1. Instead of -5, we have 0, etc. And then the final line of output just gives us the sign of these values. So for a 1, I get 1, which is, to indicate positive. For a 0, I get 0. For -7, because that's negative, I get -1. 6, 2, 5 are all positive, so I get 1, 1, 1. Then I have 2 negative values, -5 and -6 gives me -1, 0 and -1. Okay, so those are all fairly simple examples of transform algorithms. All right, so we've taken a look at for each, where each operation requires a reference to the current element and can directly work on that reference. Then transform, which has both an input range and an output range, and the output range may or may not be the same as the input range. And transform requires functions that take arguments by value and that return values when they're done. And then finally we have, or the third example we're going to look at here is this very simple little function called copy. And all the copy algorithm does is to take all of the values from some beginning range or for some input range and send those into some output range with no transformations. Okay, so this is kind of no big deal. We can use copy to copy from a vector into another vector that has at least the same size, etc. One of the cool things we can do with copy is to use what are called O-stream iterators. And an O-stream iterator can be associated with an output file or with cout, all right? And the O-stream iterator, if I use that as my output container, allows me to write values to the screen or store values into files. All right, so we give the name of our output stream iterator variable. That can be any name we make up. And then we give our output stream object, such as cout. We're also allowed, if we wish, to specify a delimiter. And the delimiter, somewhat strangely, has to be a C string. It can't be an individual character. It can't be a C++ string object. It needs to be a C string. Here's some examples. And let me show you the code. Actually, I'm going to comment out everything above here and comment back in everything below there so that we're only looking at the output for the O-stream examples. All right, so what I'm doing is creating a vector of ints v4 with these 6 values. I'm then getting the beginning and ending iterators for that vector, and I'm creating an output stream iterator that I'm cleverly calling this output stream iterator 1, OSIT1, and I'm associating that output stream iterator with cout. So when I do this copy of all of the values from the beginning of vector v4 up to one before the end of v4 into the output stream iterator, that has the same effect as writing those values one value at a time onto my output screen. Now the bad news is that this iterator doesn't have any delimiter. So the output that I'm going to get is going to be 142157 with no spaces in between. In the blue example, I am specifying a delimiter for use between the values, and so this is going to look more reasonable. It's going to be 1 space, 4 space, 2 space, 1 space, etc. And in the third example here, the green example, what I'm specifying as my delimiter is the string comma space. My idea here is that I want to get a comma and a space following each value that's displayed. Now that one's a little more complicated. Let me run this and show you what the output looks like, and then we'll talk about how we got the particular output that we did. Okay, so here, as I said, this is using output stream iterator number 1, and I do see the values 142, 157, but with no spaces in between. Then for output stream iterator number 2, I do get a space following each one. Now there's actually a space here following the 7. Okay? So if I want to display a comma after each value, one thing I need to think about is I probably don't really want to see a comma after that 7. I really only want to see commas and spaces following all of the values except for the last value. I don't want to have a comma and a space after the last value. How in the world do I do that? Well, actually, what I can do is I can say copy from the beginning of the vector up to 1 less than the end of the vector, okay? So I can stop 1 less than the end of the vector, and that gets me my 1 with comma space, 4 with comma space, 2 with comma space, 1 with comma space, 5 with comma space. So I get all of the values displayed except for the last one with the delimiter comma space after each one. Well, but that leaves the last one to display. How can I display the last one? Aha! Well, an iterator behaves just like a pointer, so I can take the iterator v4 end, which is beyond the end of the vector. I can back up 1 position so that my iterator now is at the last item in the vector, the 7. And then I can dereference that iterator to obtain the value that that modified iterator value points to, quote, points to, unquote. But the star and the minus here are simply sugarcoating, or I should say it the other way around. The star and the minus I can rewrite by using subscript notation. Remember that the subscript notation is actually syntactic sugarcoating. It's just, you know, an easier to read version of star of the quantity v4e minus 1. And so that's how I can obtain my last value from the vector, and I'm following that one by a new line rather than a comma and a space. Okay, so these are some examples of the copy algorithm, which is very simple, and also the idea of O-stream iterators with and without delimiters, excuse me, and also this notion that, remember, an iterator is a fancy kind of pointer, and for a vector iterator, you can do subtraction and you can do indirection, or you can do subscripting. Alrighty. Well, so that gets us to the conclusion of the kinds of function objects, or some of the kinds of function objects that you can use with algorithms such as for each and transform. And we also took a look at copy. There are lots and lots and lots and lots more algorithms that we simply don't have time to get into. You can count the number of times that a value occurs between some range of iterators. You can find the minimum element that exists between some range of iterators, or the maximum element that exists. You can, in fact, find the minimum and maximum by specifying your own comparison operation. So if you don't want to use just plain old less than or greater than, you can specify some different operation to use. Okay. You can find some value in a range, and what you will get back is an iterator that, quote, points to, unquote, that element. You can also do searching. You can find adjacent values. You can test whether two sequences are equal. That is, if you want to test whether one vector has values that are equal to some other vector, you can specify the beginning and the ending of the first vector and the beginning of the second vector, and you'll be told, true or false, whether those two vectors match at least up to that many values. Now, I didn't show any examples in here of sets, but one of the cool things about this equal function is you can also test whether the items in a vector are equal to the items in a set. Now, the trouble with a set is that the set contains individual unique values in ascending order. So if your vector is not in ascending order, then that won't work. However, is permutation will work. All right, so if you have a vector of unique values and you have a set of the same unique values, the set will be in ascending order. You can test whether the values in the vector are a permutation of the values in the set, and if that's true, you'll be told true, otherwise false. We can detect whether a range is sorted. We can do reversing, rotating, shuffling. Random shuffle just does a plain old what am I trying to say? Random shuffle does a uniform distribution. And we can sort, we can do binary searches, lots and lots and lots more. All right, so I will leave some of those for the homework and the rest of them for you to discover on your own time. All right, so that is it for talking about these standard algorithms.